All right, I hope you guys are doing well today. The first thing that I would like to talk about is the concept of time constants. For RL and RC circuits. So we learned yesterday, or excuse me, Wednesday, when we were analyzing RL and RC circuits, that generically speaking, for any RL circuit, we found that the natural response of such a system was given by this mathematical relationship. Y sub n of t is y at 0 minus for t less than 0 minus, and then y at 0 plus e to the negative req over leq times time for t greater than or equal to 0 plus. And very similarly, we found that for an RC circuit, our natural response was given by the equation y at 0 minus for t less than 0 minus and y at 0 plus e to the negative t divided by req times ceq for t greater than or equal to 0 plus. And it should be fairly obvious by looking at these expressions for the natural response that they are incredibly similar to each other. In fact, the only difference between these relationships is what's being multiplied by time in that exponential function during the transient condition. So engineers have developed the concept of a time constant to help quantify the exponential decay that is going on in an electrical circuit. Okay. So this is analogous to the concept of a half-life for radioactive chemicals and things like that. It's just a number that is quantifying how long it takes for our signal, in this case, to decay down to some value versus how long it takes for a radiation level to decay down to some specific value. So engineers have decided that a single time constant, and I'm going to write this down, one time constant, tau, is the amount of time needed for a signal to decay to, let me get my calculator out here so I can give this to you explicitly, 36.788% of its original value. So that may seem like a very, very strange number, but 36.788% is literally just e to the minus 1. So if we plotted something here, so this will be y sub n of t Actually, let me move that up. Y sub n of t divided by y sub n at 0 plus, so this is a ratio. And here is time on this axis. We should have a curve that is exponentially decaying from 1 down towards 0 as we allow time to elapse, right? So this point right here would be 1.00. Well, roughly right here would be 0.368. And so this would constitute one time constant, or tau. So there's a couple of reasons why a time constant is important. A, as we've already mentioned, it quantifies how quickly our signals are decaying in this system. But another reason that a time constant is important is because it essentially lets us figure out how long our steady state condition lasts. And so to sort that part of things out, I'm going to develop a table with you guys really quickly. Okay. So my table is going to look something like this. On the left-hand side, we're going to look at time measured in multiples of time constants. And on the right-hand side, we're going to look at that ratio of our instantaneous natural response versus where it started at t is equal to 0 plus. So this will be y sub n of t divided by y sub n at 0 plus. Okay. So at 0 time constants, or no time has elapsed since our switch changed states, obviously this ratio is exactly 1. Okay. At 1 tau, we have 0.368, which is just e to the minus 1. Well, at 2 tau, we have 0.135, which is just e to the minus 2. At 3 tau, we have 0.0497, so let's just call that 0.50, or e to the minus 3. At 4 tau, we have 0.0183, e to the minus 4. And the last one that we're going to look at is what's going on at 5 tau, which comes out to be 0.0067. So let's just call that 0.007, which is e to the minus 5. So what we've just figured out is that it takes a signal 5 time constants to decay down to less than 1% of its original value. So essentially, for engineering purposes, 5 time constants is infinity, because that's how long it takes for our energy storage element to transfer almost all of its energy to any resistances, bringing our system back to DC steady state. Okay. So I'm going to write that down here. It takes 5 time constants for our system to return to DC steady state. Okay. So t is equal to infinity doesn't really mean that we wait an infinitely long time to look at our system. We're just waiting potentially a few seconds if our time constant is in the order of, several microseconds, to realistically a couple of milliseconds if our time constant is on the order of microseconds, right? So it doesn't really take an incredible amount of time for us to actually reach t is equal to infinity from an engineering standpoint. It's literally just 5 time constants, whatever that time constant happens to be. So let's now develop an equation pretty quickly to determine what our time constant is going to be for an RL circuit and for an RC circuit. So I'm going to scroll up here and I'm going to look at this really quickly. So essentially, we're trying to figure out what value of t, this guy right here, is going to make that exponential function just be e to the minus 1. So would anybody care to take a stab at this incredible amount of algebra needed here? That was utter sarcasm, by the way. So what we're looking for is REQ over LEQ times something is equal to 1. Anybody care to give it a crack? All right, well, I guess I'll just give it to you. So for an RL circuit, let me make sure that L looks more like an L. Tau is simply equal to LEQ over REQ. So if we look up here really quickly, if we substitute in t is equal to LEQ over REQ, then we have REQ times LEQ over REQ times LEQ is literally just 1, okay? So it's not anything mind-blowing that's going on here. We're just looking for the value of time that makes that exponential look like e to the minus 1, okay? For an RC circuit, what we'll find is that our time constant is simply the product of REQ times CEQ, because we would have REQ times CEQ divided by REQ times CEQ, which is obviously 1, okay? So these are our expressions for our time constants for both an RL circuit and an RC circuit. And so really what would happen now to our analysis steps is we would change step number 4 from find REQ and LEQ or find REQ and CEQ to just find the time constant for the system so that we can use the exact same steps for every single problem. So before we move on to our larger topic for the day, which is the total response of first order circuits, does anybody have any questions about the concept of a time constant or anything like that? All right. So let's now talk about our total response. So what we talked about in class on Wednesday was the natural response of our system, which is how it behaves when we take any independent sources away, right? So we switched out current sources and voltage sources, and we saw how our RL and RC networks behaved while they were simply transferring energy from the energy storage element into the equivalent resistance of the system. Total response is just we are leaving sources in our system after the transient condition begins. Okay. So mathematically speaking, our total response, Y total, as a function of time, is simply going to be our natural response, Yn, as a function of time, plus what I'm going to call our forced response, Yf, as a function of time. Well, this forced response is really just whatever is going on at t is equal to infinity. Okay. So I want us to take a look at a simple RC system. Okay. So let's say that we have something akin to this. So here's some source voltage. Here is a switch. And now, instead of opening at t is equal to 0, we're having it close at t is equal to 0. Here is our equivalent resistance, Req. Here is our equivalent capacitance, CEQ. And then here is our capacitor voltage, VC, as a function of time. And that's really the only thing that we are going to be interested in right now. So I want to ask you guys a couple of questions, and these are meant to be fairly easy and straightforward. What should VC at 0 minus be for this system, where the switch is open, so the equivalent resistance and equivalent capacitance aren't connected to the voltage source at all?
0.
0. Absolutely right. Now, what will our capacitor voltage be at t is equal to 0 plus, the instant after our switch closes?
Whatever BS is.
I disagree. The reason why I disagree is because the capacitor voltage cannot change abruptly. So whatever voltage drop the capacitor had at t is equal to 0 minus, it needs to continue to have at t is equal to 0 plus. So VC at 0 minus is still 0 volts. Now, at t is equal to infinity, so a long time after our switch has closed, meaning that we've allowed our capacitor to charge, what would we expect the voltage drop across the capacitor to be?
That would be VS.
That is VS. Exactly right. So this part right here is our forced response. It is that simple. So essentially, that voltage source Vs would be considered a forcing function because it is forcing the capacitor voltage to be non-zero a long time after our system undergoes its transient condition. That's all a forced response is, okay? So if we have a DC voltage source as our forced response, or excuse me, as our forcing function, we should have a DC voltage as our forced response. What we're going to see in about 2 weeks' time is if we had a sinusoidally varying input signal as our forcing function, we will get a sinusoidally varying output signal as our forced response. But I'm getting well ahead of what we should be talking about today by talking about sinusoidal signals. Okay. So what I'm going to do now is I'm literally just going to put this information um, in a piecewise function form and see kind of how things shake out. So I'm just taking what we did in our last class meeting and seeing if I can adapt what we learned today to that. Okay. So for what it's worth, there is going to be an error here. So you may not want to write things down just yet. So my total response, actually, let's just call this VC, but this is representing my total response, should look like VC at 0 minus for t less than 0 minus. And then according to my expression up here, it should look like my natural response, which would be VC at 0 plus e to the negative t divided by REQ times CEQ. So that's my natural response, plus VC at infinity, which is my forced response for all time greater than or equal to 0 plus. Now, there is an issue with this relationship. Can anybody tell me what it is?
Is it the VC infinity?
So it's not the VC at infinity, actually. So let's look at what happens at t is equal to 0 minus here, okay? So at t is equal to 0 minus, we have VC of 0 minus, which is 0 volts, okay? So nothing wild or crazy there, is exactly what we would expect. If we were to plug in t is equal to 0 plus into this equation, this guy right here would be 0, just directly substituting in that 0 volts there. So we would have 0 times e to the 0, which is just 1, plus VC at infinity. So this winds up looking like VC at infinity right now. Let me draw that less shittily. Okay. So is our capacitor voltage a continuous function in time? No, because it abruptly changed from 0 at t is equal to 0 minus up to Vs essentially at t is equal to 0 plus. So we have to make a very slight modification to the mathematical form that we were dealing with on Wednesday in order to account for our forced response, okay? So I'm going to erase this, and now I'm going to fix it, okay? And this fix is very slight, but it is very important. Okay? So instead of having just VC at 0 plus like we had on Wednesday, now I'm going to have VC at 0 plus minus VC at infinity, e to the minus t divided by REQ over CEQ plus VC at infinity for t greater than or equal to 0 plus. So if we substitute in t is equal to 0 into this expression, we wind up getting 0 minus Vs e to the 0 plus Vs, which actually does wind up equaling 0. So now our capacitor voltage is correctly a continuous function in time. Okay. So more generally, we can say that our total response will be given by y at 0 minus for t less than 0 minus, and then it will look like y at 0 plus minus y at infinity multiplied by e to the negative t over tau, our time constant. So this expression works for both RL and RC circuits, plus y at infinity for t greater than or equal to 0 plus. So this is our generic equation for our total response problems, where again, a total response problem is just a problem where we leave sources in during the transient condition. We're going to start looking at some examples of that here in just a moment. That being said, if you have trouble identifying whether or not you should use the natural response relationship or the total response relationship, you can just use the total response relationship for literally everything. Because in a natural response system, y at infinity is 0. So you're simply adding and subtracting 0. So you'll waste a couple of seconds analyzing your circuit at t is equal to infinity to find out, oh, everything was 0, and then you'll just go on about your day. So you can actually use this particular relationship for literally every transient analysis problem in this class, and you'll be perfectly fine. Okay. So this particular equation has, once again, 4 pieces of unknown things, right? So we have to figure out what's going on at 0 minus. We have to figure out what's going on at 0 plus. We have to figure out what's going on at t is equal to infinity. And then lastly, we need to calculate our time constant. If we can find those 4 pieces of information, we can just plug that in and we will know how any current or voltage in our system is behaving. Okay. So let's work an example problem 2 if you guys are feeling squirrely, and we can call it a day after that if you're satisfied. So I'm just grabbing a random circuit analysis textbook, and I'm just going to find a problem that looks good. So let's start with something fairly straightforward here. And again, if we want to work more, we definitely can. So let's say that I have the following circuit where I'm going to have a 4 amp source here. Connected in parallel to a 3 ohm resistor. Now I'm going to have a switch over here. My switch is going to start out closed at position A, and it will move over and be closed at position B at t is equal to 0. My switch is connected to a 0.2 millifarad capacitor. And let's see over here, terminal B is connected to another resistor. So this is going to be a 6 ohm resistor. And then let's put another current source over here. So this will be a 6 amp source, like so. And let's say that I am interested in the voltage drop across my capacitor, as well as the current flowing through this 6 ohm resistor. Okay. So just to kind of explain what's going on here and to differentiate it from what we did on Wednesday, obviously when our switch changes states from position A to position B, that 4 amp source is being disconnected from the capacitor. What's different is that now we are going to have a 6 amp source that is left in and will remain in during the transient condition all the way through until we hit DC steady state again, okay? So we are not taking the source out in this case. We are effectively switching which source and resistor, for what it's worth, is influencing the behavior of the capacitor. So our process for this problem is going to be incredibly similar to what we did on Wednesday. In fact, all of the steps are going to be essentially the same. Okay. But now, step 3, which was analyzing the circuit at t is equal to infinity, will actually be important. Okay. So step 1 is, once again, analyze the circuit at t is equal to 0 minus. Okay. So at t is equal to 0 minus, we are at DC steady state. I'm going to make a note of that again, just in case you guys forgot. Which means our capacitor is going to look like what?
An open circuit?
An open circuit. Thank you, Colin. Exactly right. So I'm going to draw this circuit at t is equal to 0 minus. So here's our 4 amp source. Here is our 3 ohm resistor. Terminal A and my closed switch. Here is the open circuit representing my capacitor. Terminal B over here is open circuited. Here's my 6 ohm resistor. Here's my 6 amp source. This is VC at 0 minus, which I'm interested in finding. And this is IR at 0 minus, which I'm interested in finding. So does anybody have any thoughts on how we might determine either of those unknown quantities that we're interested in?
Would IR be equal to 0 since there's an open circuit connected to it?
So if we apply Kirchhoff's current law at that top right node, what we're going to see is that
Wouldn't it
the
be
6
6
amps of
amps?
currents, yeah, so 6 amps is going to hit this node. None of it can continue to flow to the left, so all of it flows down through the 6 ohm resistor. So that means that IR at 0 minus is 6 amps. Are you okay with that explanation, Colin?
Yes, sir. Makes sense.
Okay. So using a very similar line of thought, how would we find VC at 0 minus?
Could you do KVL around that loop?
Yes and no. The reason why I'm saying yes and no is if we did KVL around the loop, we would essentially find that VC or our capacitor is in parallel with our 3 ohm resistor, which is in parallel with our 4 amp source, which that doesn't really give us any information because we don't know what the voltage drop across the 3 ohm resistor and the 4 amp source is.
Could we do Ohm's law and do 4 times 3 because they're all in parallel?
Exactly right. So that's what I think would be a better use of our time here, is recognizing that because the capacitor is in parallel with a 3 ohm resistor, we can just use Ohm's law and say that VC is 4 amps times 3 ohms is 12 volts and call it a day. Shit. 4 amps, 3 ohms, 12 volts, and we're good to go. All right. Does anybody have any questions about the circuit analysis that we performed for this step? All right. So step number 2 is going to be for us to analyze the circuit at t is equal to 0 plus. So we are no longer at DC steady state. So our capacitor is not going to behave like an open circuit. So I'm going to draw things out again really quickly. So here is our 4 amp source in parallel with our 3 ohm resistor. Now terminal A over here is open circuited and our switch is closed at B. I'm going to leave that capacitor part blank. We'll talk about what that's going to look like here in just a moment, but it's the exact same thing we did on Wednesday, if anybody's interested. Here's our 6 ohm resistor. Here is our 6 amp source. So can any of you guys recall what we did to capacitors at t is equal to 0 plus on Wednesday?
Are they not independent voltage sources?
So that's exactly right. We're going to replace our capacitor with an independent voltage source. So I've got a voltage source right here. And for what it's worth, I'm going to make a note out here to the right. The reason why we're able to do this, and I explained it on Wednesday, but I don't mind reviewing it, is that the voltage drop across the capacitor at t is equal to 0 plus must be the same as the voltage drop across the capacitor at t is equal to 0 minus, which in this case was 12 volts. Okay. So that means the voltage drop across the capacitor is fixed at this one specific instant in time. So since the voltage is fixed and the current can be anything it needs to be, that mimics the behavior of an independent voltage source. So I'm going to make sure that the polarity of my independent voltage source is the same thing as the polarity of VC at 0 minus. And I'm also going to substitute in the value of our voltage at t is equal to 0 minus. All right. So the only thing that we actually need to find is our resistor current at t is equal to 0 plus. So does anybody have any thoughts on how we might determine that quantity?
We can do Ohm's law again.
Yeah. So it's just going to be 12 volts divided by 6 ohms, which will be 2 amps.
Is there a
Does
reason
any-
why the 6 amp source is not involved?
So we know that the 12 volts representing the capacitor is in parallel with the 6 ohm resistor, right? So that means there's a 12 volt drop over the 6 ohm resistor. So if we were thinking about things from Kirchhoff's current law context, all that really means is that the current that's flowing through the capacitor has to be 4 amps in order to make everything true simultaneously. Because if we have 6 amps flowing into the top node, and then 2 amps flowing down through the 6 ohm resistor, we must have 4 amps flowing down through the 12-volt source that is representing our capacitor in order for KCL to be satisfied.
Yes, sir.
All right. Any other questions, comments, or concerns about the analysis that we did here at step number 2? Okay, let's move on to step number 3. So step number 3 tells us to analyze the circuit at t is equal to infinity, which, since this is the first time we ever have really needed to do it, I'm going to remind you guys that t is equal to infinity represents a DC steady state condition after our transient has died out, okay? So that means our switch is still going to be closed at position B, like we had at t is equal to 0 plus, but now our capacitor is going to look like an open circuit. So redrawing our system at t is equal to infinity should look like this. We've got our 4 amp source in parallel with our 3 ohm resistor. Terminal A is still open circuited. Terminal B is still closed by the switch, but now our capacitor is an open circuit because we're at DC steady state. Here is our 6 ohm resistor. Here is our 6 amp source. We're trying to find VC at infinity and IR at infinity. So does anybody have any thoughts on how we might determine either of those quantities?
DC would be 6 amps times 6 ohms, so 36 volts.
Exactly right. So VC at infinity is just 6 amps times 6 ohms is 36 volts. Any thoughts on IR at infinity?
It would be 6 amps.
6 amps, exactly right. So none of the current from that 6 amp source can flow all the way to the left through the capacitor because it's behaving like an open circuit. So all of it had to flow down through the 6 ohm resistor. Absolutely correct. Does anybody have any questions, comments, or concerns about the analysis that we performed here at t is equal to infinity? Okay. So now we're going to move on to step number 4. Which is going to be to determine the time constant during the transient condition. Since this is an RC circuit, our time constant tau is going to be our equivalent resistance multiplied by our equivalent capacitance, okay? So if we scroll back up to our original circuit, the only capacitor that we have in our system is that 0.2 millifarad capacitor, so I believe very strongly that that is our CEQ. So CEQ is 0.2 millifarads. So now we need to determine REQ, okay? So just to remind you guys, what we're doing is we're finding the Thevenin equivalent resistance seen by our energy storage element, which in this case is our capacitor. And we're doing this during the transient condition. So I'm going to redraw our circuit. So here's our 4 amp source, our 3 ohm resistor. Terminal A is open circuited. Here's our capacitor. Since I'm going to wind up erasing it in a moment, I'm not going to bother giving it a value. Here's our 6 ohm resistor. Here's our 6 amp source. We're finding the Thevenin equivalent with respect to our energy storage element or our capacitor. So we take our capacitor out, leaving behind an open circuited set of terminals. Because we're finding Thevenin resistance, we need to turn off all of our independent sources, which means this 6 amp source looks like an open circuit. And this 4 amp source looks like an open circuit. And we are looking in through the terminals left behind when we took the capacitor out. So, what do we see?
Your only resistant in question is the 6 ohm.
Exactly right. So REQ is just going to be the 6 ohm resistor in this case. Okay, so plugging in numbers here, we would have 6 ohms times 0.2 times 10 to the minus 3 farads, where a farad is a second per ohm or an amp second per volt. We see very easily that this ohm cancels this ohm, and we're going to be left with something in seconds, which is great because the time constant just tells us how long or how much time has elapsed until it decays down to roughly 36%. So 6 times 0.2 times 10 to the minus 3 looks like 1.2 milliseconds. And for reasons that should be obvious in a moment, I'm going to find the reciprocal of tau. So that's just going to be 1 over 1.2 milliseconds, which looks like 2500 over 3 per second. So the last thing that we're going to do, step number 5, is simply plug stuff in to our generic equation. And to remind you all, our generic equation is now, y total is equal to y at 0 minus for t less than 0 minus, and it's going to be y at 0 plus minus y at infinity, e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So let's start with our capacitor voltage. So what was the voltage drop across our capacitor at t is equal to 0 minus?
12 volts.
12 volts, thank you. T less than 0 minus. So because we had a capacitor, the voltage stayed 12 at 0 plus. What was our voltage at t is equal to infinity?
36.
Yep. So we're going to do minus 36 e to the negative. So t over tau is the same thing as t times the reciprocal of tau. And the reciprocal of tau is 2500 over 3. That's why I choose to find the time constant and then flip it over. So 2500 over 3 times time plus y at infinity was once again 36 volts for t greater than or equal to 0 plus. And now, just for the hell of it, I'll simplify this down a little bit. So we would have 12 t less than 0 minus negative 24 e to the minus 2500 over 3t plus 36 volts for t greater than or equal to 0 plus. For our resistor current, we had 6 amps, if I'm remembering correctly, at t is equal to 0 minus. Then we had, let's see, 2 amps at 0 plus, and 6 amps yet again at infinity. And once again, simplifying this, we just have 6 amps for t less than 0 minus, and then negative 4 e to the minus 2500 over 3t plus 6 amps for t greater than or equal to 0 plus. So looking at what's happening here mathematically, we can kind of think of, since the capacitor, or excuse me, the resistor current started at 6 amps and then it ends at 6 amps, during the transient condition, the capacitor is effectively just stealing current away from the resistor while it charges up. And then once it becomes fully charged, that resistor current settles back to 6 amps. Okay. Would you guys like for me to work another example problem? All right. Well, I'm fine with not working anymore because it was, excuse me, this lecture is so incredibly similar to what we did on Wednesday anyway. So I will hang out on Zoom if you guys have any questions regarding your in-class assignment. If not, I hope you have a great weekend and I will see you on Monday.